Good afternoon. Uh, I'm Silve from Georgia Tech, and I'm going to talk about a fuzzing framework called Hydra, which is capable of finding semantic bugs in file systems. So before I start my talk, I want to show you a little demonstration. So I'm going to run a single instance of fuzzer on my laptop, fuzzing F2FS file system for crash consistency. And let's check the result at the end of the talk. So let me ask you this question. Can file systems be bug-free? Of course not. And there are two main reasons. First of all, code base is too huge. So if we take a look at those three most widely used Linux file systems, ext4 has about 40,000 lines of code, and Btrfs and XFS has about 100,000 lines of code. And if we include the size of the common VFS layer, the size even grows. On top of that, code base is evolving, which means that developers are actively managing the code base. So they keep adding new features, new functionality, patching the patches of bugs, and so on. So as a result, in 2019, more than 100 bugs were reported in those three file systems. And of course, these bugs are devastating. They carry a bad effect. Data could be lost or corrupted, or your program could be experiencing a runtime error, or it could even open a window for security vulnerabilities. So previously, to find and eliminate those kind of bugs, people have tried regression testing, model checking, or verified file systems, or even fuzzing. So the regression testing has a problem that it can only test the known test cases. We can't expect them to find new bugs from the new code that are introduced in the file systems. Also for model checking works, if it's a static model checking work, they fundamentally suffer from high false positives. And also, even though it's dynamic, it also shares the same problem of known test cases problem because it can't test the model against the entire input space. And verifying the entire file system could be very favorable approach if it's done correctly. However, there still is a large unverified parts, and most of the bugs come from these parts. And what about fuzzing? Actually, fuzzing is the approach that we're taking because feedback-driven fuzzing is pretty much a complementary solution to all those approaches. So we can produce effective test cases on the fly, which means we don't need to undergo the known test cases problem anymore. Also, it's proven to be scalable in practice, so we don't need to write the entire new file system, or we don't even need to try to verify. We can just directly test the existing file systems as is. So known file system fuzzers like KFL or syscaller, these are basing on the virtual machines to fuzz the kernels, or our previous work, Janus, which bases on the library OS. They're doing pretty good jobs. So Janus discovered 90 memory safety bugs from file systems alone in 2018. But the problem we see here is that existing file system fuzzers focus only on memory safety bugs. In reality, file system bugs come in various flavors. So memory safety bugs are only a minority of those, and the rest are semantic. There could be crash consistency bugs, specification violation, logic bugs, or concurrency, and so on. So we want to take advantage of fuzzing, apply it to finding semantic bugs in the file systems. And here's the challenge of doing so. So in general, semantic bugs are deemed to be harder to detect because the key idea in traditional fuzzing is that crashes are valuable feedback to the fuzzers. Say we're fuzzing for memory safety bugs in the target program. Fuzzer generates an input, feeds it to the target program, and if there's a memory safety bug, it's going to crash. And the crash is going to send some sort of signal, like segmentation fault, as a feedback back to the fuzzer. Thus, fuzzer can detect the detect the memory safety bug in the target program. On the other hand, semantic bugs are silent. They leave no trails. So say we're fuzzing for a specification violation. Fuzzer is going to do the same thing. But even though there's a bug in the target program, one of the functions could be returning a wrong return value internally, but fuzzer is not aware of this. And thus, this bug is not detected. So what we need here is a checker, which could go through the test case and check for each and every return value internally of the functions. And then if there's a mismatch of the specification, it could send feedback to the fuzzer so that such kind of bug can be detected. So our claim here is that accurate checker for each bug type needs to be integrated to the fuzzing loop in order for semantic bugs to be found through fuzzing. that's precisely what we consider when we're designing Hydra framework. So this is the overview of Hydra here in a very, very high level. And the input generator is a variant of an AFL, and it actually, you can find more detail about how we generate our input in our previous works paper. And the test case generated is basically a combination of a file system image and system call trace. When this test case is given to the libOS test executor binary, it mounts the image, executes the system calls, and also dispatches a checker, which checks for the existence of the bug. And while doing so, feedback is provided back to the input generator. So from the test executor, as we're relying on the Linux kernel library, we statically link it to our executor binary. We can collect file system specific code coverage and send it back to the input generator. Also, we have, from checkers, we have checker-defined signals, which could be as simple as a Boolean value showing that the test case triggers a bug or not. So we want to stress here that as a framework, Hydra takes care of so many things. It takes care of automated input space exploration, generation of the test cases, executing the test cases, incorporating various checkers, also takes care of the feedback. While the framework provides those services, a tester, a developer, can focus on developing a specialized bug checker which is of high quality. So thanks to this separation of concern, developers may focus solely on describing the bugs of their own interests. Another strength we want to stress is that Hydra is extensible through pluggable checkers. So we ourselves could also focus on writing a crash consistency checker called SymCQ after designing this entire framework and plug it in, and it seamlessly worked to detect several crash consistency bugs. And for specification violation, we could utilize existing checker oracle called CivilFS. It's provided as a binary, and with only a few lines of code for integration, we could plug it in and then find some of the specification violations in the tested file systems. And for finding logic bugs, there already are kernels built-in file system checks and assertions that we could enable and then just find logic bugs. Also for the memory safety bugs, we could utilize the kernel address sanitizer without any modification and found several bugs. So as you can see here, it's really extensible to other types of bugs by plugging in relevant checkers. If you have a bug type on your mind, you could bring an existing checker, or you could write on your own and then plug it in and then find the checkers with the assist of the Hydra framework. So now I'm going to show you how Hydra actually works when it's trying to find the crash consistency bugs by utilizing the SymCQ checker. So SymCQ is a symbolic emulator of the crashing states. So like how the real file system is implemented, it keeps track of the in-memory and on-disk states. So as an input, a list of system calls is given, and with the initial states from the fuzzer, from the input generator, I mean. And as an output, it produces the list of legitimate post-crash states. And checking errors is like this. Given the test case from the input generator, the libOS executor first mounts the image, runs the system calls, and then crashes. And then mounts the crashed image again to get gamma, which is a concrete state of the image, which has just recovered from the crash. Simultaneously, we run SymCQ. So SymCQ symbolically emulates the test cases to generate sigma, which is a set of legitimate states. And now checking for the crash consistency error boils down to checking whether gamma is a member of sigma or not. If it is, it's not a bug. If it isn't, it's a bug. Here's a more concrete example. So for the purpose of demonstration, I brought the simplest test case generated by the fuzzer, but indeed it was a bug in F2FS. So on the right-hand side, there are internal data structures that the emulator maintains. So we keep track of the tree in memory on these data structures, and we also keep track of the snapshots, which we later use to enumerate possible crash states. So when the first make directory of A happens, you can see that the tree is updated to have the new inode with the name mapped to A, and this change is only applied to the in-memory side. This is precisely what the real file systems do. When something happens, it's only applied to the in-memory side, and when some persistence operations like sync, fsync, or fdatasync happens, then those changes are flushed to the disk. And emulator does the same. So when sync happens, all metadata is flushed to the on-disk data structures. And then when change mode happens, we are changing the permission mode of A from 775 to 600. And so the history of those changes are maintained, along with the new metadata is written in the in-memory side. And then we fsync A. So now we have a guarantee that this inode number 1 of name A should have permission mode of 0600 after it crashes and then recovers. After emulating all those 4 file system operations, it's time to enumerate the legitimate post-crash states. And this is how it's done. First, we check validity of each and every snapshots we had. And snapshot number 0 can easily be dropped because we know for sure that inode number 1 is persisted through the sync operation. We can find the information from the on-disk data structures. And the second snapshot, snapshot number 1, is valid because it does not violate any of the persisted states. So after checking the validity of snapshots, we can generate possible crash states by combining the valid snapshots with the information from on-disk and in-memory data structures. In this example, we only have one state available. So now that we have the set of legitimate states, or sigma, and we also have the crashed concrete state gamma, which comes from the executor, we can do the membership testing to check for the existence of the bug. So in the red box, this is the actual concrete image that once crashed and then recovered. So if you check the stat of A, we can see that the access mode is still 775, and this doesn't belong to any of the post-crash states. So we can conclude that none of the states, we can conclude that this is a real bug, real consistency bug. So we reported this bug, and this bug is patched in the latest kernel. And now if you evaluate, Hydra is highly effective in finding semantic bugs. So we have found 36 new semantic bugs, along with 33 memory errors as a side effect. And 9 of which were crash consistency bugs. We utilized our own SymCube crash consistency checker, and 23 logic bugs with 4 spec violations. And interestingly, one of the crash consistency bugs were found in the FSCQ file system, which is a verified crash-safe file system. So the bug was about directory being lost when there's a crash if another irrelevant file is truncated. And the developer responded that this is because they have used unverified helper function in their implementation. And Hydra does quickly explore the input space because basically it's a fuzzer. So even though the throughput of Hydra is bound by the performance of each checkers, it's still faster than VM-based approaches. Also, it generates better test cases. If we compare the code coverage for fuzzing ext4 file system for 12 hours, we can see that Hydra outperforms syscolor and KFL. We can also compare the test cases of Hydra against the bcube's test suite. So bcube is yet another crash consistency testing tool which generates test cases by enumerating file system operations. So it limits the input space with bounds. For example, they assume that the number of core file system operations has to be less than or equal to 3. Otherwise, the input space will be too huge for testing. But still, Hydra generates test cases on the fly. And when these two test cases are compared against the code coverage for 12 hours of fuzzing ext4 file systems, bcube's enumerated test cases exhaustively tested ext4 but still explored less code. And as a result of that, bcube missed all of the crash consistency bugs found by Hydra in combination with SymCube. Yes, so in summary, Hydra is an extensible fuzzing framework, and we have already open sourced our code in the provided link. And it discovered hard to detect semantic bugs, 9 crash consistency bugs, 4 POSIX violations, 23 logic bugs. And as future extensions, we're thinking of integrating more bug checkers, for example, data race checker, or add support for distributed file systems. And before I wrap up, it's time to check the fuzzing results. So in 14 minutes, it indeed found 18 crash consistency bugs. And we can see the logs here. So these are raw format logs of the bugs. So we can pick one of the logs and process it to see the cause and effect. So I just randomly picked one of the logs. So there, if I cat the report, it says there's a mode mismatch in directory foo So the emulated mode is 6000. So the mode should have been 6000, but after crashing and recovering, it was still 755. So let's check the code to see what happened. Hope you can see it. It's a little bit complicated, but still. So v3 is foo. And here we open directory foo and store the file descriptor in v12 and set x attribute. And here we're changing the mode of v3, which is a directory foo, to 3072 decimal, which actually is octal 6000. And then we truncate this directory. And then remember we opened and stored the file descriptor in v12, and the last operation is fsyncing. So that we need to ensure so that it ensures that the changed mode is persisted to the disk. So I'm going to run this test case generated by the fuzzer in my VM, which actually runs the tested kernel here. Make a new file, paste it. And because of this CSRQ on the last line, it's going to crash. It's going to reboot right away after fsyncs. It's basically simulating a crash. So I want to compile it. So now we have the binary, and then first mount the image. This is the base image we have. So I'm going to run the compiled test case. And it's restarting, rebooting right away. And then let's hope we can see that the permission mode of foo is not persisted. So if I mount it again, get into it, and tree dot. So I'm going to stat foo. And yeah, the access mode is not persisted, even though we had an explicit fsync call to this directory. Yeah, so indeed, we have found a real crash consistency bug in a short time. Which means Hydra is highly effective and efficient as well. So that will conclude my talk, and I think we can go on to the Q&A session. Thank you.
Nauman from Google. What do you do with the bugs once you found them? Do you report them somewhere?
Sorry, I couldn't hear you. Could you speak up?
What do you do with the bugs when you find them?
We report the bug. So as the fuzzer generates the concrete POC, we just replay it ourselves and then report to the developers so that it could be patched.
I have a question. What kind of effort does it take to write the checkers? Like, can you provide hints to developers to do that more effectively?
Sorry, could you repeat that?
What kind of effort does it take to write the checkers, the specialized checkers?
So there are papers about single checkers. So yeah, it does need some effort to be written. So for writing crash consistency checkers, we had to precisely emulate the POSIX specification and also implement file system specific interpretation of the crash guarantees. And that was one big challenge of doing so.
Thank you. Let's thank the speaker again. Oh, sorry, there's another question.
Yeah.
Hi, Joe Tuchuk, AWS. I was wondering, so that particular test case you just showed us seemed, as you mentioned, quite big.
Mm-hmm.
Do you know for that bug, is that a minimal test case?
Could you repeat the last part?
Is that a minimal test case?
No, we do have a minimizer as a service, but the case I've shown you is not minimal. And if you run the minimizer, which takes advantage of the delta debugging technique, then you're going to be able to see the minimized test case.
Roughly how small that particular one, do you happen to know, gets to?
Sorry, what was that?
That particular test case, roughly how small does the minimizer get it to?
Sorry, could you repeat once more?
What percentage of the test case goes away for that particular one, roughly?
So in our experiment, we could observe that minimizer actually minimizes the number of operations from around 70 to 20 or less than 10. Yeah.
Thank you.
Thank you.
All right, let's thank the speaker again.